Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fourth lecture of the 8th module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the Galerkin finite element solution of steady convection diffusion equation in one dimension using three noded or quadratic bar elements. So the given problem is described here. So we shall consider the steady convection diffusion transport equation, and our degree of freedom is small u. So the domain of interest is of 1.5 unit long. We are given the convective velocity small c as 1 meter per second. The source term is non-homogeneous, its value is 1, and then we have essential boundary conditions at both the ends, and these both EBCs are of homogeneous type. We shall discretize the domain by using quadratic bar element. For this example, we shall consider three quadratic bar elements. We shall show our results for two different values of Peclet numbers. Peclet numbers 1 and 5 will be considered. Solution of the given problem. We shall use three numbers of quadratic bar elements to discretize the 1D domain of 1.5 meter length. So this is our problem domain. This is omega. So this is x equals to 0, x equals to 1.5. So here we are given homogeneous EBC at x equals to 0. So u0 equals to 0 and u at 1.5, this is also 0. Our governing equation is C del u del x equals to nu del 2u del x2 plus Sx. Since it is an ODE in one dimension, this can be written as, may be written or expressed as C du dx equals to nu d2u dx2 plus Sx over omega. We have been given C equals to 1 meter per second, Sx equals to 1 unit, and then we shall use three quadratic bar elements. So this is a quadratic bar element, element E. So local node 1, local node 2, local node 3. So our domain is 1.5 meter long. So in this case, with three elements, our mesh size will be 0.5 meter. So these are the parameters. We shall consider Peclet numbers 1 and 5. So let us discretize the domain. The mesh is shown as x equals to 0, x equals to 1.5 meter. This is the x direction. We have three elements, element 1, element 2, element 3. Our global nodes are 1, 2, 3, 4, 5, 6 and 7. So this is our delta x. The element we have already shown. So here the element is arbitrary element E with local nodes 1, 2 and 3. The mesh size is delta x equals to 0.5 meter. Our degrees of freedom are u1e, u2e At the third node, it is U3E. So we generate the IEN array here. IEN array E A. We have 3 elements, 1, 2, 3. Our local nodes are 1, 2 and 3. So our global nodes we have for element 1, these are 1, 2, 3. For element 2, these are 3, 4 and 5. And finally for element 3, these are 5, 6 and 7. Now we generate the ID array. We have homogeneous EBC at both ends. Let's generate the ID array. So here our first element, then we have the second element, and then we have the third element. We have total 7 global nodes. So global node 1, equation number is 0. Global node 2, equation number is 1. Global node 3, the equation number is 2. Global node 4, equation number is 3. Global node 5, equation number is 4. And global node 6, the equation number is 5. At global node 7, the EBC is given of homogeneous type, so equation number is 0. So these are our global equation numbers, capital P or capital Q. So here we generate the ID array as A versus ID A. We have global nodes 1, 2, 3, 4, 5, 6 and 7. So our ID values at nodes 1 and 7, they are 0. At the remaining nodes, the equation numbers grow as 1, 2, 3, 4 and 5. Now we shall generate the LM array. Generate the LM array. So here we have E, A, I, N, E, E. E is 1, 2, 3. A is 1, 2, 3. Our I is 1 at all the nodes. So our element level equations will have 3 values. So we have 3 element level equations, 1, 2 and 3. For the first element, our equation numbers are 0, 1 and 2. For the second element, these numbers are 2, 3 and 4. For the third element, these numbers are 4, 5 and 0. So our degrees of freedom are U1, U2, U3, U4 and U5. So we shall get a 5 by 5 matrix equation system. So here P and Q, they vary from 1 to 5. So our assembled matrix equation system will be of the form K P Q Q Q equals to FP. So we have generated all the preprocessor arrays. Let us go to the processor array. Here this is delta x by 2 and the mesh size we show here for this third element as delta x. We have already derived the weak form and element level matrices and vectors for this problem. So the convection diffusion equation is the first chapter where we deal with fully fluid flow problems. in the heat conduction problems, we dealt mostly with the solid mechanics. If the fluid is fixed, or if we discuss only about the solids, then we go for conduction mode of heat transfer. In the 7th module, we had hyperbolic partial differential equations, where we had wave motion in a fluid. And here in chapter 8, we are dealing about the fluid flow problems. So here we already know the convection matrix, diffusion matrix, mass matrix expression. For the steady state problem, we do not require the mass matrix. So for the quadratic bar element, the element level equation is Kije Uje equals to Fie, or Keue equals to Fe. This gives us Cije plus Dije Uje equals to Fie, or Ce plus De into Ue equals to Fe. So for this case, our I is varying from 1 to 3 and J is varying from 1 to 3. Here Ce is the convection matrix at the element level, De is the diffusion matrix at the element level, and Fe is the load vector at the element level. So our matrix can be written as C11E, C12E, C13E, C21E, C22E, C23E, C31E, C32E, C33E, plus D11E, D12E, D13E, D21E, D22E, D23E, D31E, D32E, D33E into the derivative vector U1E, U2E, U3E equals to F1E, F2E, F3G due to the source term, plus F1E, F2E, F3E due to the EBC, since in this problem we only have the EBC. So this is our finite element. So this is local node 1, local node 2, local node 3. Our degrees of freedom are U1E, U2E, U3E. The mesh size is delta X. So here our element level equation is Ke Ue equals to Fe, or we have K11E, K12E, K13E, K21E, K22E, K23E, K31E, K32E, K33E. Then we have U1E, U2E, U3E. In the right hand side we have the components of the load vector F1E, F2E and F3E. So these two matrices, they construct the Ke terms. So the convection matrix and the diffusion matrix, they construct the stiffness matrix. So Ke, this is equals to Ce plus De. Now let us substitute the already calculated values. So C11E, this is minus c by 2, 2c by 3, minus c by 6, minus 2c by 3, 0, 2c by 3, it is c by 6, it is minus 2c by 3, and here it is c by 2. Our D11E, this is nu into 7 by 3 delta x minus 8 by 3 delta x, 1 by 3 delta x minus 8 by 3 delta x, 16 by 3 delta x minus 8 by 3 delta x. Then finally we have 1 by 3 delta x minus 8 by 3 delta x and 7 by 3 delta x. So we have our left hand side matrix terms. The DOF vector is U1E, U2E, U3E. Then we have the load vector components. These are S into delta x by 6, 4S into delta x by 6, S into delta x by 6, plus we have the EBC contribution from the source term F1E, F2E, F3E only if E belongs to the boundary. So this EBC load vector, this vector exists only for E equals to 1 and E equals to 3 or the boundary elements. Now we have already discussed that the local Peclet number or the element Peclet number PEX equals to C delta x by 2 nu, which can be used to represent nu in terms of the local Peclet number. So nu equals to C delta x by 2 PEX. So now we combine these terms and we generate the final element level matrix equation system. So the final element level matrix equation system is here. In the convection matrix we have minus C by 2, 2C by 3, minus C by 6, minus 2C by 3, 0, 2C by 3, C by 6, minus 2C by 3. We have finally C by 2, and nu it is C delta x by 2 Peclet number. So this is C into delta x by 2 into local Peclet number. So this is 7 by 3 delta x. Then we have C into delta x by 2 PEX into minus 8 by 3 delta x. Then we have C into delta x by 2 Peclet number into 1 by 3 delta x. In the second row we have C delta x by 2 PEX into minus 8 by 3 delta x. Then we have C delta x by 2 PEX into 16 by 3 delta x. Then we have C delta x by 2 PEX into minus 8 by 3 delta x. In the last row we have C delta x by 2 PEX into 1 by 3 delta x. Then we have C delta x by 2 PEX into minus 8 by 3 delta x. The final term is C delta x by 2 PEX into 7 by 3 delta X. So we have our convection and diffusion matrix terms. So this is with the DOF vector U1E, U2E, U3E. Then in the right hand side we had S delta X by 6, 4S delta X by 6, S delta X by 6. Then we have the EBC contribution. This was F1E, F2E, F3E, EBC if applicable. Now we can further simplify this element level equation as, we can write it as minus C by 2 plus 7C by 2 PEX. Next we have 2C by 3 minus 8C by 6 PEX. The third term is minus C by 6 plus C by 6 PEX. Now in the second row we have minus 2C by 3 minus 8C by 6 PEX. The diagonal term we shall have 16C by 6 PEX. The last term in the second row we have 2C by 3 minus 8C by 6 PEX. In the third row we have C by 6 plus C by 6 PEX. Then we have minus 2C by 3 minus 8C by 6 PEX. Then we have C by 2 plus 7C by 6 PEX. So this is our assembled element level stiffness matrix KE. So this represents the KE multiplied with U1E, U2E, and then we have U3E. In the right hand side we have S into delta X by 6, 4S into delta X by 6, and S delta X by 6, plus we have the EBC counterpart F1E, F2E, F3E due to EBC if applicable. Now we have C equals to 1 meter per second and S equals to 1 unit. Our Peclet numbers, they are having two values 1 and 5. So we can simplify this above expression by inserting the values of C and S. So this may be rewritten as our C is 1, so this is minus half plus 7 by 2 PE, then we have 2/3 minus 8 by 6 PE, then we have minus 1 by 6 plus 1 by 6 PE. In the second row we have minus 2 by 3 minus 8 by 6 PE, then here we have 16 by 6 PE. In the last term of the second row we have 2/3 minus 8 by 6 PE. In the third row we have 1 by 6 plus 1 by 6 PE. Next we have minus 2/3 minus 8 by 6 PE, and finally we have 1 by 2 plus 7 by 6 PE. So we have constructed the stiffness matrix as a function of local Peclet number. These are U1e, U2e and U3e for the degree of freedom vector. In the right hand side, you can put the value of S. So S was 1. Delta x is also 0.5. For the time being, we keep delta x value. So this is delta x by 6, 4, delta x by 6, and then we have delta x by 6. So this EBC portion we shall use directly and we don't continue it anymore. We shall straight away implement the essential boundary condition. So here we have the combined stiffness matrix KE or the stiffness matrix. This gives us KE UE equals to FE. So now we have the element level entries. Now we can perform the assembly and we can generate the global matrix equation system. Now we can perform assembly of the element level entries. So our LM array, we need to make it once more. So here we have elements 1, 2, 3, the local nodes 1, 2, 3, the IDOF 1, 1, 1 and NEE 1, 2, 3. For the first element, our equation numbers were 0, 1 and 2. For the second element, those were 2, 3 and 4. And finally for the last element, those were 4, 5 and 0. So we draw the mesh once more. So this is element 1, this is element 2, this is element 3. So equation number is 0, equation number 1, equation number 2, equation number 3, equation number 4 and equation number 5, equation number 0 at the boundary. So this is the mesh size. Now we write our assembled coefficient matrix. So capital K equals to, it will be a 5 by 5 matrix. The first term is K11. So K11, this is K221. K11 equals to K221. K221, this will be 16 by 6 PE. So this will be 16 divided by 6 PE. Now we have the next term K12. K12, this is K231. K12 equals to K231. K12 is K231. K231 is 23 minus 8 by 6 PE equals to 2/3 minus 8 by 6 PE. 2/3 minus 8 by 6 PE. Then we have K13. So K13 will be 0. K13, it is not present in any of the element 1 and 3 simultaneously. Similarly, K14 and K15 will be 0 because 1 and 4, similarly 1 and 5, they do not belong to any common element. So K14 and K15, they are all zeros. 0, 0, 0. So we go to the next row now. So in the next row, we shall have K21. K21 equals to K321. K321. K321, this is minus 2/3 minus 8 by 6 PE. Minus 2/3 minus 8 by 6 PE. Then we have K22. K22 equals to K331. K331 plus we have K112. K112. K331, this is half plus 7 by 6 PE. This is half plus 7 by 6 PE plus K112 is minus half plus 7 by, this will be 7 by 6 PE. So this is 6 PE. So K112, this is minus half plus 7 by 6 PE. Minus half plus 7 by 6 PE. Then we have K23. K23 will be K122. K23 equals to K122. K23 equals to K122. 2/3 minus 8 by 6 PE. 2/3 minus 8 by 6 PE. Then we have K24. K24 will be K132. K24 will be K132. 132. So K132, this will be minus 1/6 plus 1 by 6 PE. Minus 1/6 plus 1 by 6 PE. Then K25. K25 will be 0. K25, this is equal to 0. Then we go to the third row, K31. K31, this is 0. Then we have K32. K32 is K212. K32 equals to K212. K212, it is minus 2/3 minus 8 by 6 PE. Minus 2/3 minus 8 by 6 PE. Then we have K33. K33 equals to K222. K33 equals to K222. K222, it will be 16 by 6 PE. 16 by 6 PE. Then we shall have K34. K34 will be K232. K34 will be K232. K232, it is 2/3 minus 8 by 6 PE. 2/3 minus 8 by 6 PE. And final term in the third row, this is K35. K35, it is 0. Then we move to the fourth row, K41. This is also 0. K41 is 0. Then we go for K42. K42 is K312. K42 equals to K312. K312, this is 1/6 plus 1 by 6 PE. 1/6 plus 1 by 6 PE. Then we have K43. K43 is K322. K43 equals to K322. K322, it is minus 2/3 minus 8 by 6 PE. Minus 2/3 minus 8 by 6 PE. Then we have K44. K44 equals to K332. K332 plus K113. K113. K332, it is half plus 7 by 6 PE. Half plus 7 by 6 PE plus K113 minus half plus 7 by 6 PE minus half plus 7 by 6 PE. Then we have K45. K45 is K123. K45 equals to K123. K123, this is 2/3 minus 8 by 6 PE. 2/3 minus 8 by 6 PE. And then in the last row, we have K51, K52, K53, all of them are 0. K51, 0, K52, 0, K53, 0. Then we have K54. K54 will be K213 equals to K213. K213, this is minus 2/3 minus 8 by 6 PE minus 2/3 minus 8 by 6 PE. And finally we have K55. K55 equals to K223. K223, this comes as 16 by 6 PE. This is 16 by 6 PE. So we have assembled the global coefficient matrix due to convection and diffusion. We can represent it now as a function of local Peclet number. So now we have constructed the global stiffness matrix based on the convection and diffusion terms as a function of the Peclet number. From here we can represent the global matrix as capital K equals to, the first term is 16 by 6 PE, 16 by 6 PE. The second term is 2/3 minus 8 by 6 PE, 2/3 minus 8 by 6 PE. Remaining three terms are all zeros. Then in the second row we have minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE. Next, the diagonal term is 14 by 6 PE, 14 by 6 PE. The next term is 2/3 minus 8 by 6 PE, 2/3 minus 8 by 6 PE. Then we have minus 1/6 plus 1 by 6 PE, minus 1/6 plus 1 by 6 PE. Then K25 is 0 value. Then we have K31 as 0. K32, this is minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE. K33, this is 16 by 6 PE, 16 by 6 PE. K34, it is 2/3 minus 8 by 6 PE, 2/3 minus 8 by 6 PE, and the K35 is 0 value. Then we have K41 is 0, K42, this is 1/6 plus 1 by 6 PE, 1/6 plus 1 by 6 PE. Then we have K43 minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE. Then we have K44, this is 14 by 6 PE, 14 by 6 PE, and the final term is 2/3 minus 8 by 6 PE, 2/3 minus 8 by 6 PE in the fourth row. The last term in the fifth row, this will be 0 for K51, K52 and K53. So these are 0, 0, 0. Then K54, it is minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE, and finally the diagonal term is 16 by 6 PE. 16 by 6 PE. So we have the 5 by 5 assembled matrix as a function of the Peclet number. Now if we take Peclet number equals to 1, if PE equals to 1, then K equals to 16 by 6 2/3 minus 8 by 6 0 0 0. Then we have minus 2/3 minus 8 by 6. Then we have 14 by 6. Then we have 2/3 minus 8 by 6. Then we have minus 1 by 6 plus 1 by 6. Then it is 0 0 minus 2/3 minus 8 by 6. It is 16 by 6. This is 2/3 minus 8 by 6. It is 0. In the fourth row we have 0. Then we have 1/6 plus 1/6 minus 2/3 minus 8 by 6. 14 by 6. Then it is 2/3 minus 8 by 6. In the last row we have 0 0 0 minus 2/3 minus 8 by 6. Then we have here 16 by 6. So we can see that for the Peclet number of one value, one of the term becomes 0. The matrix which we get, we see that it is a pentadiagonal matrix and it is certainly an asymmetric matrix. The assembled matrix is pentadiagonal and asymmetric. After simplification, we can see here we have 8 by 3, then 2/3 minus 8 by 6, this is minus 2 by 3, then we have 0 0 0. In the second row we have minus 2, then we have 7 by 3, here we have minus 2/3 0 0. In the third row we have 0, then we have minus 2, then we have 8 by 3, then we have minus 2 by 3 0. In the fourth row we have 0 1/3, then we have minus 2 7 by 3 minus 2 by 3. In the fifth row we have 0 0 0 minus 2 8 by 3. So after putting the value of Peclet number, particularly for Peclet number 1, we see that our matrix, it contains 4 diagonals. For PE equals to 1, the assembled matrix contains 4 diagonals. Now we construct the assembled load vector. So we have our element here, element 1, element 2, element 3. So equation number 0, equation number 1, equation number 2, equation number 3, equation number 4, equation number 5, and equation number 0. So our load vector, it is a 5 by 1 vector. So we have u1e, u2e, u3e, u4e, and u5e. Our load vector f, this is a 5 by 1 vector, f1, f2, f3, f4, and f5. So here we get our vector components. f1 is f21 minus k211 u11. The next is f2 is f31 plus f12 minus k311 u11. Next is f3, it is an internal element, no effect from the EBC, so this will be f22. Next is f4. So f4, it is part of the boundary element 3, so here we shall get f32 plus f13 minus k133 u33, and finally the last term f5 will be f23 this is from the source term minus k233 u33. Now our f11, we have the load vector Fe equals to delta x by 6, 4 delta x by 6, and delta x by 6. So we have f1e, f2e, and f3e from here. So f21, this is 4 delta x by 6. So this is 4 into delta x by 6 minus k211. Our element level term k211, this is minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE, minus 2/3 minus 8 by 6 PE into u11, this is 0. Then we have f31 is delta x by 6 plus f12, this is also delta x by 6 minus k311, this is 1/6 plus 1/6 PE. So this is 1/6 plus 1 by 6 PE into 0. Then we have f22. f22 is 4 delta x by 6. 4 delta x by 6. Then we have f32. This is delta x by 6 plus f13 is also delta x by 6 minus k133 u33. k133, this is minus 1/6 plus 1 by 6 PE. This is minus 1/6 plus 1 by 6 PE into 0. The final is f23. This is 4 delta x by 6 minus k233. k233, this is 2/3 minus 8 by 6 PE. This is 2/3 minus 8 by 6 PE into 0. So here the contribution due to EBC, it disappears. So we have 4 into delta x by 6, then we have 2 into delta x by 6, 4 into delta x by 6. Here we have 2 into delta x by 6 and 4 into delta x by 6. This is our assembled load vector. So we can now solve for this matrix equation system, which we can write it. Now the assembled matrix equation system may be written as Ku equals to F. So we have the K matrix already ready. So this was 8 by 3 minus 2/3 000. 8 by 3 minus 2/3 000. In the second row we had minus 2 7/3 minus 2/3. Minus 2 7/3 minus 2/3 0 0. In the third row we had 0 minus 2 8 by 3 minus 2 3. 0 minus 2 8 by 3 minus 2 8 by 3 minus 2/3 0 minus 2/3 0. In the fourth row we had 0 1/3 minus 2, 0 1/3 minus 2, 7/3 minus 2/3, 7/3 minus 2/3. In the last row we had 0 minus 2 8 by 3, 0 minus 2 8 by 3. Then our degree of freedom vector is u1, u2, u3, u4, u5. The right hand side load vector, here we can put delta x equals to 0.5. So we can write it as 4 into 0.5 by 6, 2 into 0.5 by 6, 4 into 0.5 by 6, 2 into 0.5 by 6 and 4 into 0.5 by 6. Here, these are the global variables, the global degrees of freedom. So certainly E should not be here. So these are U1, U2, U3, U4 up to U5 as the global unknown quantities. So here we have shown the assembled load vector values. So here we have got the numbers for the load vector F, and then we solve it for the Peclet number 1 case. So here this is our assembled matrix of 5 by 5 size, and then we have the Gauss-Seidel solution for this case. We have found our results. These results, they do not show any oscillatory behavior. The results obtained for PE equals to 1 do not exhibit any oscillatory behavior. Similarly, the problem can be solved for PE equals to 5. We can predict oscillatory solutions for PE equals to 5 since this value is outside the stability limit. We conclude today's class here. We have shown GFEM calculations for Peclet number 1 flow subject to 1D convection diffusion problem. We have used 3-noded or quadratic bar elements. The results for PE equals to 1 do not exhibit oscillations. In the similar way, PE equals to 5 cases can also be computed. For today's lecture, I recommend the textbook by Professors Donia and Huerta. Thank you very much for attending my lecture.